In this investigation, your teacher gives you some string, a set of masses, a protractor, a stopwatch, and asks the class to investigate the motion of a pendulum. Your class contains 3 lab groups, and lab group number 1 collects the following data. They measure how the mass affects the period. What conclusions could be drawn from the data gathered by group number 1? Notice that the masses vary greatly, and the period very, very little. So I think we can draw a conclusion that the mass does not greatly affect the period, but we do see a little bit of difference in the period. And the reason I think that we might be able to account for that is twofold. So if this is the pendulum, and we have a big mass on it, versus this pendulum, which has the same length of string, but a little mass on it, we can see that the length of the pendulum, which goes from where it's connected to the ceiling to the middle or the center of mass of the bob, would be longer with the bigger mass. So maybe that's part of the error. Another thing that is possible is when you attach the big mass to the pendulum, maybe it stretches the string out also, just a little bit. And so both of these would result in the period being a little bit longer. But for the most part, mass has no effect on the period of a pendulum. Group 2 collects data on how the angle affects the period, and you can see that for the most part the angle does not affect the period when we're at small angles, but at larger angles we start to see an effect. In class we derived an equation for the period of a pendulum, which was 2 pi rad L over G, and so you might think that the angle should have no effect, whereas here we do see some effect from the angle. And that's because when we developed this formula, we used a small angle approximation where we said sine theta equals theta for small angles. And that's why we're having some difference here when we get to 75 degrees and 90 degrees. In any event, the question asks, what is group 2's dependent variable and how do you know? So group 2 is changing the angle. That's the independent variable, and what changes because of what they manipulate is the period, and so the period is the dependent variable. Because this is the quantity that changes based on our manipulated variable. So in the last slide we talked about how the period is equal to 2 pi rad L over G. If I want to make this in the form of a line, like y equals mx plus b, I would write this as the period is equal to 2 pi over rad g times rad L, and there is no y-intercept. And so if I plotted t on the y-axis, and if I plotted rad L on the x-axis, I would get a straight line. Another option is to square everything. If I square everything, I have t squared equals 4 pi squared over g times L. So I could also plot t squared on the y-axis and L on the x-axis. So either t versus rad L or t squared versus L will yield straight lines. Your lab group is now given a motion sensor that connects to a display and determines the horizontal position of the mass as a function of time. The display shows the following graph of motion. On the graph, place an A where the mass has a maximum acceleration, and an S where the mass has a maximum speed. We know that for simple harmonic motion, the maximum speed will come when the mass is at its rest position, and that's true for a pendulum or for a mass on a spring. That right in the center where x equals 0, or where theta equals 0, the speed is going to be a maximum. So I'll put an s here, or you could put it here, here, or here. Now in both the mass on the spring and the pendulum, the maximum acceleration is when the object is furthest from its rest position. So at x equals negative a, or x equals a for a spring, or when theta equals theta max, or theta equals negative theta max. That's where our acceleration is going to be the greatest, so I could put an a over here, or over here, or over here, here, or here.